Dear students, welcome to the second session of our chapter 5 States of Matter. In the previous session, we have gone through the gas laws, that is, Boyle's law and Charles' law. Today, we'll discuss the problems related to that Boyle's law and Charles' law first. Let's see a problem. A weather balloon has a volume of 175 liter. When filled with hydrogen at a pressure of 1 atmosphere, calculate the volume of the balloon when it rises to a height of 2000 meters, where the atmospheric pressure is 0.80 atmosphere. Assume that the temperature is constant. So this is our problem and we have to calculate the volume. Now what are the things we have given in the question? First we have to write that one and then we have to check which formula we have to apply. According to the Boyle's law, what is the equation? First we have to see and all given things are there. We have to note down. So the given thing is what? P1. What is P1? The pressure is given at 1 atmosphere. And the P2 value, that is the atmospheric pressure is given as 0.80 atmosphere. That is P2 value. Then what about the V1 volume? Volume 175 liter and V2 we have to calculate. So this is our given thing and what we have to find. Now according to the Boyle's law, the temperature is remaining constant. So we can write it as what? P1 V1 is equal to P2 V2. And from here we have to calculate the V2. So which formula? We have to just rearrange this formula. So we'll get what? V2 is equal to P1 V1 by P2. And substituting the values, we'll get P1 1 atmosphere into 175 liter divided by 0.80 atmosphere. After equating, we'll get the answer as 218.7 liter. So this is what the volume of the balloon when it rises to a height of 2000 meter. The next problem, if it is to find the temperature. Let's see the problem. A sample of helium has a volume of 500 centimeter cube at 373 Kelvin. So volume is given, temperature is given. Calculate the temperature at which the volume will become 260 centimeter cube. That means two volumes are given and one temperature is given and the other temperature you have to calculate. And which formula we will apply here? Already it is given that the pressure is kept constant. So we have to use the Charles law, right? That is V1 T1. V1 by T1 is equal to V2 by T2. That formula we have to apply. So the given things are V1 is equal to 500 centimeter cube. V2 is equal to 260 centimeter cube. T1 is 373 Kelvin and the other one T2 we have to find out. Using the Charles law, we can write the formula as what? T2 is equal to V2 into T1 by V1 after rearranging and substituting the values 260 into 373 by 500. We will get the answer as 194 Kelvin. So this is how we are finding out the temperature at which the volume becomes 260 centimeter cube. Now let's see one more problem. A certain amount of a gas at 27 degrees Celsius and 1 atmospheric pressure occupies a volume of 25 meter cube. If the pressure is kept constant and the temperature is raised to 77 degrees Celsius, what would be the volume of the gas? Keeping in mind that pressure is constant, we have to use Charles' law. So the temperature is getting changed here. Therefore, what formula will use? V1 by T1 is equal to V2 by T2. And what all things we are having here? V1, how much volume? 25 meter cube. V2 we have to find out. T1 is given as 27 degrees Celsius. It should be changed into Kelvin. So you have to add with 27 to 73.15 and you are getting an answer of 300.15 Kelvin. Same way, the T2 is also given in degrees Celsius, 77 degrees Celsius. It should be converted into Kelvin. So you have to add up with that 77 to 73.15 and we get 350.15 Kelvin. Substituting these values in our Charles law equation, we'll get 25 meter cube by 300.15 Kelvin is equal to V2 divided by 350.15 Kelvin. From there, V2 value will be 350.15 into 25 divided by 300.15 and we will get the answer as 29.16 meter cube. That means the gas would occupy a volume of 29.16 meter cube. The third gas law is Gay-Lussac's law or the pressure temperature relationship. The mathematical relationship between the pressure and temperature was given by Joseph Gay-Lussac and that's why the name is Gay-Lussac's law. It states that at constant volume, the pressure of a fixed amount of a gas varies directly with the temperature and it can be mathematically represented as P is directly proportional to the temperature or when we remove the proportionality sign it can be P is equal to constant into temperature or it can be written as P by T is equal to a constant and here we have named it as K3. This relationship can be derived from the Boyle's law and the Charles law. The pressure versus temperature, that is, temperature is taken in Kelvin scale, graph when we plot at constant molar volume or at constant volume, like in the figure we have drawn, each line of this graph is called isochore. That means we are plotting a graph with pressure versus temperature when constant volume is there. So each line represents what? It is a isochore. And we know that with the increase in temperature, the pressure also is getting increased. So it is directly proportional to each other. The next law is Avogadro's law. It states that equal volumes of all the gases under the same condition of temperature and pressure contain equal number of molecules. That means the temperature and pressure are constant here. So what is the variables here? The volume and the number of moles. So we can say that the volume of a gas directly depends upon the number of molecules in it. So we can represent in what way? V is directly proportional to small letter n, that is number of moles. To remove the proportionality sign, we use a constant here, K4. So it becomes V is equal to K4 into n. And as we know that 1 mole is equal to what? 6.022 into 10 raised to 23 molecules. That is said to be what? Avogadro's number. Now, if a question is to calculate the number of moles in a gas, which formula we will apply? The number of moles is equal to given mass by molecular mass. Given mass by molecular mass. This we have learnt in class 9th. So here m is the mass of the gas and m small letter m and capital M is the molar mass or molecular mass. So if we use the same form, that is V is equal to K4 into N, instead of that and that is number of moles, we can use here what? M by M. So the equation changes to V is equal to K4 into M by capital M. And this equation can be rewritten as what? Capital M is equal to K4 into M by V, or it can be written as K4 into D. Why? Because D is the density, mass by volume is what? Density. So indirectly we can say what? Density is directly proportional to its molecular mass or molar mass. Hence this law that follows the Boyle's law as well as the Charles law and the Avogadro's law is said to be what? Ideal gas. Ideal gas. So a gas which is said to be ideal gas should obey Boyle's law, Charles' law and Avogadro's law. Now let us talk about the ideal gas equation. Just now we have said about the ideal gas. a gas which obeys Boyle's law, Charles' law, and Avogadro's law is said to be ideal gas. So related to that, if a equation comes, it is said to be what? Ideal gas equation. Let's combine all the three laws in one single formula. According to this, the Boyle's law is volume is directly proportional to 1 by P. Charles' law, volume is directly proportional to temperature. Avogadro's law, volume is directly proportional to number of molecules. Now here all the terms we can see that volume is directly proportional, volume is directly. So we can just combine these three equations to one and we'll get what? V is directly proportional to NT by P. And to remove the proportionality constant, we have kept a constant R. So it is changed to V is equal to R into NT by P. And R is said to be the proportionality constant. So we can again rearrange this one and we'll get what? PV is equal to nRT. From there, if we want R is equal to PV by NT. So R is said to be a name, that is gas constant or universal gas constant. R, the proportionality constant, is having a particular name in this ideal gas equation, that is said to be gas constant or universal gas constant. At STP, standard temperature pressure, the value of R becomes 8.314 Kelvin per mole. And in this equation, we can say that equation of state also. And applying this one, we can understand that it can be written as what? P1 V1 by T1 is equal to NR, or P2 V2 by T2 is equal to NR. Right? This one we can get as what? P1 V1 by T1 is equal to P2 V2 by T2. This equation is called what? Combined gas law. Combined gas law, as it contains 5 variables, and it is also known as a special equation of quartz-Lesanes. That is other name. So this equation P1 V1 by T1 is equal to P2 V2 by T2 is said to be the combined gas law. Now here we can understand that R is constant in both the cases. R is a universal constant and N is what? The number of moles. So in both the cases it may vary or it is equal. So depending upon the gas we can write that value. So what is the variables here? P1, V1 and T1, or P2, V2 and T2. Now if there is a relationship between the density and the molar mass, how we can explain that thing? We know that ideal gas can be arranged as follows. N by V is equal to P by RT. The equation which we have written before, PV is equal to nRT, it is written in this form. N by V is equal to P by RT. Replacing the N, that is the number of moles, by given mass by molar mass, we will get this equation as what? M by capital M V is equal to P by RT. And as we know that mass by volume is density, we can replace that value and we can write it as what? D by M is equal to P by RT. For calculating the molar mass of a gas, we can use the formula capital M is equal to molar mass is equal to dRT by P. So this is a relationship, that is molar mass and the density. The equation is here. M is equal to dRT by P. D is the density, R gas constant, T temperature, P volume. Thank you. We'll continue in the next session.